Hi everyone. Today we shall be dealing with some properties of conductors when they are placed in certain electric field, and that the whole soul of all this topic is called electrostatics of the conductors. So we shall be discussing some different points under this electrostatics of the conductor, and the very first point is that when a conductor is placed inside an external electric field, the net electric field inside the conductor is always zero. Okay? The net electric field inside any conductor is always zero. And let's see why this happens so. So I am not writing the whole heading, only speaking about this. So imagine this is a conductor placed inside a electric field. Okay, this is the electric field pointing from my left to right, and its intensity is E. We know there are so many free electrons inside the conductor. What happens to those free electrons under the effect of this external electric field? So the electrons roaming randomly inside the conductor are attracted by the positive side of the field. Because why this is positive side, I am saying, when you are producing this field, so there must be something in the background which has a positive charge, so that the electric field is being formed or being produced by this away from it. That's why the direction is taken this way, and this is the positive background. So all the free electrons start jumping means they start coming towards this region, and simultaneously the same amount of positive charge starts accumulating on the other side, so that the so formed charge combination produces an electric field inside the conductor, but in opposite direction of the E outer. Outer means external field, and this is E internal field, or I must say this is some P for polarized, and that electric field is called induced electric field. And this accumulation of, that is movement of charge from one to other side by the effect of this electric field keeps on doing so unless the inside developed electric field EP becomes equal to that of the external electric field. Okay? When exactly this happens means the EP field produced by this accumulation of charge, and this accumulation is done by the externally applied electric field, right? So at this particular condition means this particular condition has to come anyhow. Whatever is the strength of the electric field, the conductor itself produces exactly equal to that of that external field by shifting the positive and negative charge according to the scene in front of you. So when this happens, all negative charges or maximum number of negative charges have come this way and positive this way, so that the electric field produced inside the conductor of its own property, when this equals the outer electric field, it means inside the conductor the net electric field E will be exactly equal to 0, because this field is left side towards left side and this field outer is towards the right side. So both being equal and opposite simply cancel each other, and the net electric field is 0. This 0, how does this 0 comes? This is a vector sum of two quantities यहाँ पर. So E outer, the mod of E outer is equal to mod of E induced field, and that's why the net electric field inside the conductor becomes 0. Okay, this is the first property, that inside the conductor electric field is always 0. Now property number 2, at any conductor at its surface, when it is being charged, the electric field is always perpendicular to its surface. That is, for particularly this position, the electric field would be this way, so that this is 90 degree. For this particular reason, the electric field is this way, so that this angle is 90, and so forth. That is, at every point the electric field will be perpendicular to the surface. Remember, these are the points we have to simply keep in mind so that we can apply them according to the situations. And derivations are simply, you have to go through the book. I shall not be going into the derivations, how this happens, for only sake of reason, as we have already proved that if electric field does not go this way, if I am using the word if electric field is not this way, it means it is say inclined at any particular angle, that is, the angle is not 90 degree, then what happens? This electric field will have a component. Suppose this is along this way, it means this angle is theta. So if this angle is theta, this electric field must have two components, that is E sin theta, this is sine component, and that will be what? Cos component, and that is E cos theta. This is something that is coming out from this electric field if it is not perpendicular to the surface. So this component is not equal to 0. It means this component is not equal to 0 according to our concept. But the book says, or the theory says what? Okay, this component has to be 0. Why this has to be 0? If any small charge placed at its surface, it will be moving. But in practical situation, no charge placed on the charged conductor moves along the surface. So if something is not moving, it means there will be no force acting on this, and if no force acting on that, it means no electric field will be there. It means, again indicating that is the horizontal component of the field, that is, this has to be 0. And if this gets, that is horizontal component gets 0, then what happens? This cannot be 0. So cos theta must be 0, and cos theta, if it is 0, then theta must have to be 90. समझ में आ रहा है? So this angle, that is electric field, was, we supposed that electric field is this way, but actually what happens? The electric field is not this way, rather this is perpendicular to the surface. So this is property number 2. Electric field at any point on the surface is always perpendicular to the surface, or in other words, electric field is always normal to the surface. Property number next is the inside any conductor. Inside any conductor, the potential is always constant. Okay, potential is always constant. This is very simply can be proved. That is, suppose this is any conductor. We have seen that the net electric field is 0 from the first property. So it says that the potential is equal to constant inside the conductor. Maybe this is charged, or this is placed in any external electric field, whatever. If it is charged, then also, and if it is not, then also. We have a relation, that is dV over dr is equal to minus E. If I take the magnitude only, then let minus be related. So if there is no electric field inside the conductor, that is what? dV over dr equals to 0. dr cannot be 0, so dV has to be 0. And dV is what? Change in the potential at different points. So for any 2 points, any 3 points, dV will be 0. It means V is equal to constant. This is property number third. Inside any conductor, the electric potential is always constant. Okay. Property number fourth. It says that when a conductor is placed in an external electric field, right, it cannot contain any excess amount of charge. It cannot contain any excess amount of charge inside it. That is, whatever charge it is given, all charge goes to the outer surface. If it is charged, all the charge means what? What do you mean by charged? All the charge, somebody is embedding charge on it, and those all those charges simply goes to the external surfaces or outer surface. It means it does not include any charge inside it. The proof is that very simple. According to Gauss law, what is flux? E dot ds, and that's equal to q over epsilon naught. And we are saying that there will be no excess amount of charge inside the conductor. So when this is done, suppose this total surface area of this conductor is S, then this E is for constancy is taken out. Then when we solve this, we get E into S, and that is equal to Q upon epsilon naught. Okay, and in the previous first topic, we had proved that the net electric field inside the conductor is 0. Net electric field inside the conductor is 0. Then logically, from the first point, if I put that quantity equals to 0, that is 0 into S equal to Q over epsilon naught. It means this cannot be 0, epsilon naught cannot be 0, then obviously Q has to be 0. And what this Q is, we already assume that this is the total charge enclosed by the interior of the volume or the conductor. This is a simple part of this whole volume. So the fourth property is that no conductor can have excess charge inside it when it is either charged or it is placed in any external electric field, and all the charges, whatever happens, it goes out. Okay, this is property number fourth, and next property we will be having, that is fifth. The value of electric field at the surface of any charged conductor is given by sigma over epsilon naught, and that is the n cap. I am not going into the derivation of this. Once you go through the book, it will be clear to you. The fifth property is that the magnitude or the direction of the electric field on the at any point on the surface of the conductor is always given by sigma over epsilon naught. Okay, this is our fifth property. So we have mainly covered all the properties. So we have one more, that is last or sixth property. That is, suppose I have a conductor of this shape, and this is placed in any electric field or this is being charged. Suppose I have placed this in an electric field. According to the electric field concept, the field is this way. So electrons will accumulate in a position or in a direction opposite to the electric field. Okay, it means all the electrons must be accumulating this side, that is left side, and all the positive charges will be accumulating this side. Okay, according to the first point or first property. When this placed in electric field, charges inside it rearrange themselves. Okay, now it says that the charge density sigma, that is Q over, or I can say dQ upon dA, is not a constant. Rather, sigma is a variable at the surface. It means the value of charge density at different points will be different. Simply, we are having negative charge on this side, so sigma will be what? Negative. These are positive regions, so the charge density on this side will be positive. Okay, this is very simple. Positive due to positive charge accumulation, and sigma will be negative due to negative charge accumulation. One more thing that is important. Suppose if the curvature of the body at any region is very small, say this part is this part has a very low radius of curvature. It means you must be getting the idea of low radius of curvature. But obviously this region can be a part of a small ball, and this region can be a part of another big ball. Can I assume this? You must be getting what I mean, because this so curved place has been taken out and then added to this system, and that part has been taken out from a small ball. Okay, so its radius is say r1, and this segment of the body has been taken out from another bigger ball of radius say r2, and r1 is less than r2, right? It means this region has low radius of curvature and this region has high radius of curvature. So sigma for this particular region will be higher. That is, charge density, that is sigma 1, will be higher than sigma 2. You must be getting 1 or 2. Okay, this is related to region of r1 and sigma 2 is related to r2. Sigma 1, that is in this more curved region, is high, and this is low, because it gets a large quantity, large area, so all the charges distributed in a larger region. Okay, and this small particular region, in this particular region, the r being small, the charges accumulate more, so the charge density will be higher at this particular position. Okay, so these are the 6 points you have to go through, and these will be very essential during the study of electrostatics, and especially in the case of application of the all terms we will be speaking, and especially numericals. Okay, just to go through the NCERT book, please. This is very important and very characteristic property of the electrostatics. That's why the topic is called Electrostatics of the Conductors. So if we don't understand these all properties, we'll be filling so many problems in dealing with all these topics. Okay, hope you might have got this. Till then, till the next video, goodbye.